Okay, so problem 3. Problem 3, it says by applying Pythagorean's theorem using the two-dimensional version twice over, prove the length r of a three-dimensional vector is r squared equals x squared plus y squared plus z squared. Basically showing that Pythagorean's theorem extends to the third dimension, which is probably something you've seen in Calc 3 if you've taken that yet, or multivariable calculus, or if you've worked around with three-dimensional coordinate systems. And here we want to show why that's the case. And because I am such a bad drawer, what I did is, this is on my notes, like my handwritten notes, when I had the help of rulers and whatnot. This is the picture I would struggle to draw for 5 minutes, and now I have it drawn. So perfect, beautiful. Let's start by looking at this part. This bit, that's not a very good color now, is it? Let's see if I can get a better color. This bit right here, maybe green shows up a little better, a little bit. This bit is the line segment from the origin to point B. Okay? Now, when we look at this part right here, which is, let's try this. This line here, that will go parallel with our x-axis. And that'll also be perpendicular to our z-axis. So that's going to form this right angle here. So we have, if you were to look at just this part, just this triangle, this is just a triangle. So we can find the point O to B. The line segment OB, because this is the hypotenuse, right? I'm going to drop the line segment notation. We can say O to B squared is equal to the square of our other two sides, which, well, one side is right here. So that's O to A squared. And then the other side is just A to B. So AB squared. Okay? Here's the thing. Point O to A, that's coming out at us at the Z direction. Right? So that is really... O to A represents how far out of the page or into the page our point P is over here. This point P, that is represented, at least the Z component, how far in or out of the page is, by O to A. So I can replace O to A with just Z squared. Likewise, using the same logic, this point A to B, that represents the x-coordinate of point P. So that tells us our x. So using the same logic, we can replace that with x squared. Okay? So just to summarize, we drew this picture of from the origin to some point, right? And then we drew, well, I drew, before I did this, another vector that's a projection of r, but down on, let me get a different color, down on here. Then we looked at this as a triangle, a two-dimensional triangle, and we were able to come up with this equation, OB squared equals OA squared plus AB squared. And OA represents just the Z component of our point, and AB is just the X component. So we could say OB is just the square root of Z squared plus X squared. So this expression right here describes this length. That's going to be important because, in a sense, what we have is another right triangle, okay? Now, what we really want to know is O to P. From the origin to the point. We want to know about that. That's the point that we're interested in. But if you look, we really have another triangle right here, don't we? It's just another triangle where O to P is our hypotenuse. And the other legs of our triangle is O to B squared plus what? B to our point. So we have this side, which represents this bit. And then we have this side of the triangle, which is just B to P squared. Okay? But we just solved for O of B. That's all this stuff. So we can substitute that in. OB squared is just the square root of z squared plus x squared plus what? Well, B to P squared. Well, B to P is what? What's this line here represent? That represents how high up or how far down vertically point P is, because y is our up and down axis. If that's the case, then B to P is really just y. So B to P squared is y squared. So this is just y squared. And O to P, so this distance, is really just vector r, isn't it? So this is really r squared equals, well, if we square the square root, we just get what's inside. And then just rearranging to make it in the order that we normally see it. R squared equals x squared plus y squared plus c squared. So we can see that the Pythagorean theorem, in a way, extends into the third dimension. And we saw this by breaking it down into two-dimensional cases. Well, essentially a one-dimensional case and then a two-dimensional case, right? So we looked at this one. When I say this one, get the right color. We looked at this one, and we looked at this one. And using those two triangles, we used this one first, just so we can find this length. And then using that, with our knowledge of this length, we're able to find r. So pretty straightforward. Hopefully that makes sense. And I'll post more here soon.